All right, section 14.3, we're going to talk about activation energy and what exactly activation energy means and what does it and how and does it apply to our reaction rates that we've been studying. So, as we've talked about before, generally, as the temperature increases, so does the rate of reaction. So, as the temperature increases, the rate of the reaction is going to increase because the molecules are moving faster and you're going to have more collisions. Well, because the rate of the reaction increases with temperature, that means K is temperature dependent. K is going to depend on your temperature. So if we, in a chemical reaction, bonds are broken and new bonds are formed. Right? Remember, molecules can only react if they collide with one another. This is key. Right? Molecules have to collide with one another to react. No collisions, no reaction. So what we have here is molecules must collide with the correct orientation and with enough energy to cause bond breakage and formation. So what's that saying is it takes a little bit of energy for bonds to break and collide. If this energy is not present in a reaction, your reaction's not going to be able to take place. So you have here before the collision, during the collision, after the collision. However, it takes energy for the collision to occur. It takes energy for these molecules to move around and collide. And that energy is called the activation energy. And that's the minimum amount of energy required for the reaction to take place. It's abbreviated EA. Now, it takes a small bit of energy for these molecules to collide. That's the activation energy. Think of it as you're putting on a green, but you have a huge hill in front of you. You have to be able to putt the ball over the hill. If you don't putt the ball over the hill, you're not going to be able to put the ball in the hole. So that hill is the activation energy. Same thing applies for chemical reactions. You have to be able to find enough energy to start the reaction, and that's the activation energy. If you don't have enough energy to start the reaction, you're not going to get a reaction or you're not going to put the ball in the hole. So now we can kind of visualize what it takes here. If we have an example, I don't really like this. That's we're gonna kind of just this will be much better off explained in class. I'll explain that diagram in class. But what you can see here is we have activation energies. All right, the high point's the amount to activate the energy. The higher the temperature, the lower the activation energy, simply because you have more molecules. All right. So what we can do here is we can mathematically solve for the activation energy. There are a handful of equations that can help us solve for the activation energy. And one of them is right here. The fraction of molecules, F, is equal to E, and this is our mathematical E to the negative EA over RT. EA is our activation energy, R is our gas constant, and T is our temperature. And remember, we got to deal in Kelvin. Now, the Arrhenius equation is the more important of these two equations. And when we solve for the Arrhenius equation, we can find a correlation between K and EA. K, remember, is the rate constant. A is something new. A is the frequency factor. E is mathematical E to the negative EA. EA is the activation energy. R, remember, is our gas constant, and T is our temperature. Now, since we're dealing with the beautiful world of mathematics, we can rearrange this equation. The natural log of K is equal to negative EA over R times 1 over T plus the natural log of A. That lines itself up with 2. Y is equal to mx plus b. We have a perfectly linear equation. Therefore, if K is determined experimentally at several temperatures, we can calculate EA on a slope. So if we have T If we have K and we have T, we can solve for EA because EA is essentially the slope of that graph. So remember, EA over R is the slope of an activation energy or Arrhenius equation graph. So natural log of K versus 1 over T, Y, and X. Our slope of such graph would be equal to negative EA over R. So that kind of sums up the Arrhenius equation real quickly. Last thing that I want to talk about for chapter 14 is reaction mechanisms. And you guys, we typically think of reactions happening all in one step. Well, that's not necessarily the case. Reactions can occur all at once, or they may occur in several small steps. Each one of those small steps is known as an elementary process. So, if we look at reaction mechanisms, what you can see here is it'll show you the rate for a particular reaction. A to the products is K is A plus A is K to the A squared. And you can see here that it's called the molecularity of a process. So we're unimolecular, bimolecular, bimolecular. All right, and you can figure really that out by solving for, all right, adding up your exponents. You have one exponent, unimolecular. Two exponents, or the sum of your exponents is 2, bimolecular. 1 and 1 here is 2. Termolecular would be 3, and on we go. But I want to just kind of expose you to, in multi-step reactions, usually one of the steps is pretty slow. One of the steps is pretty slow, and one of them is much faster. However, what you have here is the overall reaction cannot occur faster than the slowest step. So think of it as cars, kind of cars in traffic. And you have 3 steps here. They can get slowed in step 1, they can get slowed in step 2. But the reaction cannot go faster than the slowest reaction. And this is called the rate determining step. The slowest reaction is going to determine the rate of all of the reactions. So here's just kind of a good example. I'm not going to go into great detail with that, but you have a slow step and you have a fast step. And your reaction cannot go faster than the slow step. And we'll talk more about this as we get into chapter 15. Last thing I want to talk about, going through all these fast initial, slow initial steps, is there are 2 things I want to talk about. Catalysts and enzymes. Catalysts increase the rate of reaction by decreasing the activation energy. So what a catalyst does is essentially lowers that hill to putt over for a golf ball. But a catalyst doesn't affect the overall reaction. It doesn't actually react in the reaction. It just simply lowers the activation energy. So you can see here in the red you have a large activation energy, but in the blue with the catalyst you have a smaller activation energy. So it takes less energy to start the reaction, and therefore the reaction is actually going to go quicker. So catalysts can speed up the reaction. An enzyme are catalysts in biological systems. So an enzyme is anything that could exist in the body that's going to speed up a biological reaction. And that's more of a biochemistry thing, but I just wanted to give you brief exposure to that. So that is the end of chapter 14 and the end of section 14.3. We'll talk more about this in